I've got a chemical reaction that's right here, this is a secondary alkyl halide. It's undergoing stereochemical inversion. We know this because it's going from R to S. And now we want to see how is each one of these variables going to influence the reaction rate. So let's start with our first one here. What happens if we replace the bromobutane, the 2-bromobutane, with 1-bromobutane? You want to take a guess? What's going to happen to the rate? By the way, let's draw really quickly what 1-bromobutane looks like. This is a bromine that's at carbon 1, and then it's touching 2, 3, 4. So it's got something like this. So compare the structure against what's drawn up here on the board. What do you think is going to happen in the rate? Yes, you do. Think about the alkyl halide, right? So what is this alkyl halide at the top? Yes, exactly. 1, 2. Why? How do we classify this one? This is a primary Rx. So we would expect to see an increase in the reaction rate, right? Why? Because steric bulk slows the reaction down, so removing carbon groups speeds the reaction rate up. It becomes easier for the nucleophile to find the electrophilic position. That's the point. All right, let's try another one. What happens if we replace R2-bromobutane with tert-butyl bromide? Let's sketch that one out really quickly. Tert-butyl group. You remember what a tert-butyl group is? Tert-butyl with a bromine like this. How do we classify that one? Slower. So what's the classification of the electrophile or the alkyl halide? Primary, secondary, or tertiary? It is tertiary. Excellent. And so we are increasing in steric bulk around that electrophilic position. So we should see a very sharp decrease in reactivity. Very, very sharp. All right, what happens if I replace bromine with an I? Good guess, but actually, it actually slightly increases the reaction rate. And the evidence of this is that you'd find out that bromine is a really bad base, but I- is an even worse base, right? Exactly. But remember, as you go down, so they're going to have similar properties with each other. But as you go down the periodic table, you start to increase in leaving group ability. The group gets bigger and bigger and bigger, and it's easier for it to fall off. And if it's bigger, it tends to be more stable. It's more content existing as an anion. Okay, so an I- in solution is more, let's see, it's less basic than a Br minus. So that's a good trend to just kind of know. CLs, pretty good leaving groups. Fluorines are horrible leaving groups, and that's because fluorines have a really strong affinity for forming covalent bonds with carbon. So it doesn't really like to break that bond at all. Chlorines are great, bromines are great, and iodines are even better. Problem with iodines, though, is they're very, very light sensitive, so you have to actually do them in the dark. You have to set up the reaction where you have kind of like aluminum foil around it to keep light out. And that's because the iodine-carbon bond is so weak that if you shine light on it, it will actually break into individual free radicals. And that's a big problem when that starts to happen. So you make them in a lab. So iodine itself is fine, but then once you attach it to a carbon, you have to keep it in the dark to the best of your abilities. So you don't. How do you do what? Oh, it's easy to do it. The way we know that it's happening is that we can monitor the chemical reaction with light on and with light off, and we can find out that more byproducts form in when the light is on versus when it's off. And so when that's happening, there must be. Oh, how do we know if it's complete? Well, it turns out the products that we actually make are stable. So this would be so we would just measure how much product is basically formed over the course of the chemical reaction, usually. It would be hard to measure how much I- or how much the alkyl halide is in here One other way that we could do it is that if we knew how many moles of the nucleophile was in there, we could measure how much that's been consumed over time as well. So there's plenty of ways to monitor. That's a great question. I'm glad you asked that. All right. What happens if we replace Br with OCH3? We just talked about this. What's going to happen to the rate? Think about OCH3. Good leaving group, bad leaving group. Bad leaving group. It's a great base. So Br minus is more basic than minus OCH3. So what's going to happen to the reaction rate? It is going to decrease considerably here. What if we swap out the nucleophile, this is methane thiolate, and we react it with butyl thiolate? What do you think is going to happen to the reaction now? Should slow the reaction down. Why? That's it. As we start to increase the size of the nucleophile around the nucleophilic position, so we say that a SCH3 minus is smaller than, I guess this would be S1, 2, 3, like that.